Okay, so welcome back to the next session of the Ellis workshop on 7 Secure AI. We have exciting lineup of speakers. I will start with maybe 1 or 2 minutes just talking about the Ellis PhD program, because in past years we found that many of the attendees were interested to know more. So it is a sort of pan-European program with one sort of application place. So you can send an application to a single, in a sort of certain timeline, which I will show, to a one portal, and then sort of it gets sent and it gets seen across the whole Europe in the machine learning, in the leading machine learning labs and by sort of leading machine learning researchers across Europe. Here are more information. This is the website. You can check it yourself. There is sort of nice video talking more about the program, and sort of stories of also what the students doing after. And the important part is, if you want to know more, is how to join as a student. And I will show there's an important is the timeline. So typically the applications are in October. So October this year, 2026. You send the application, then there are reviews, and for those who pass the first round, there are interviews happening in January and mid-February. That would be 2027, and then decisions are in sort of late 2027. So we highly encourage you to apply, and there are 3 tracks, which I will mention. There's academic, where you have an advisor, like a main lab, where you do the PhD, but also you have a co-advisor where you spend 6 months in another lab. So it's sort of collaborative, exciting. You get to see another lab. There's also industry track, typically local, where you spend some time in a local sort of company. You have a co-advisor from the company. Typically, you work on high impact research problems from inspired by specific application domains. And there is a new interdisciplinary track where people work on high impact problems in biology or chemistry or physics, which are sort of you have co-advisor in a different discipline. And with that, if there are any questions about it, you can also ask, because some of the speakers are like advisors in the programs. So, and we can also answer in the chat. And with that, I will finish here. I'll stop sharing. And I will give word to Nuria, who is going to introduce the next speaker.
Thank you, Joseph. If there is any quick question about the PhD program, maybe they can ask now, or if it's just something quick. Otherwise, you can reach out to us also offline.
Yeah, or put it in the chat.
And put it on the chat. Yeah, and then we can answer. Yeah, we can type it. All right. So while Krishna is sharing his screen, I will introduce him. Krishna Gummadi is a scientific director at the Max Planck Institute for Software Systems and a professor of computer science at the University of Saarland in Germany. He received his PhD in 2005 and his bachelor's in 2000 from the University of Washington, the PhD in the US, and then from the Indian Institute of Technology, Madras, the bachelor's degree. His recent research focuses on understanding and building social computing systems that are fair, accountable, explainable, and transparent. So it couldn't be more aligned with this workshop. His work on fair and transparent machine learning, on online social networks and media platforms, on internet access networks, and on peer-to-peer systems has been widely cited, and his papers have received 15 best or outstanding paper awards, including also some Test of Time awards. He is also the recipient of an ERC Advanced Grant on Foundations for Fair and Social Computing. He is a fellow in the Ellis Human-Centric Machine Learning Research Program, and today he is going to talk to us about trust and AI agents. So all yours, Krishna. You have about 20, maximum 25 minutes, so we can leave some time for questions. Thank you.
Absolutely. Can you hear me?
We can.
Good. Perfect. Thank you, Nuria, for your kind introduction, and thanks everyone for inviting me. It's my pleasure to actually present some work that we recently started engaging in. And as many people these days in machine learning, we started looking at certain trust issues that come up in the context of large language models, and that's what I'm going to talk about. So the title of my talk is In Agents We Trust, but Who Do Agents Trust? This title immediately poses a question, a very simple question, which is what exactly or when exactly does an AI model become agentic? What do I mean by the word agentic here? So to understand this, here is my way of thinking about AI agents. It may not be the only way, but this is my perception or the way in which I'm dealing with it in this talk. So if you think about a lot of online platforms that are out there, whether it is digital public spaces, like Facebook, social media platforms, Instagram, TikTok, what have you, or digital marketplaces like Uber, Lyft, or Kickstarter, or what have you, or in decision support systems, you have a variety of different types of AI models that are used. They range from search and recommender AI to match and market making AI to risk prediction algorithms and so on. Now, the distinction that I would like to make is that there are, of course, by AI models, what we mean is some sort of a neural network in case if it is a deep learning model, or a transformer in the case of a large language model. But it is important and useful to distinguish between AI models and computing architectures that embed these AI models on these platforms. And what the computing architectures do is they make the models, or they give the models agency. That is the way in which you design the hardware and the software rules to embed these AI models in a broader platform, and the sort of the framework or the rules of the game that the deployers define for how these AI models can interact with other AI models, and as well as humans, ends up determining how much agency these models have. So let me give you a little bit of more concrete examples of what I mean by this term AI models having agency. So let's consider the first example scenario, which is increasingly something that many of you might have seen, which is LLMs, or these language models, are being used as front ends for search. Sometimes this is also more broadly viewed as retrieval augmented generation, which is one where the language model is actually fetching some documents in some database, which might well be the entire web search or the corpus of web documents. And then it's using the information from the retrieved information from the documents, and it is fusing it with its own parametric knowledge, that is the knowledge that is embedded in the neural network, to generate the final response, right? So let's consider a simple example of this. So for this, I took screenshots of my own interactions with such, where AI models are being used as front ends for web search. So this is about 8 months ago. I landed in the Berlin's airport, and I had a question that I typed in my mobile phone. I asked, does Deutsche Bahn Berlin plus city ticket that I had, does it cover the trip all the way to the airport, which is actually on the outskirts of the city of Berlin? And then I was very happy when Google AI Overview, rather than just returning some links that I had to browse through and figure out what the answer is, responded by saying, yes, Deutsche Bahn plus Berlin plus city ticket includes travel to this thing. I was actually very surprised. I wasn't expecting it to be that decisive, and I was very happy. But just before I got on, I somehow wanted to double check this because I had somebody tell me before that this might not be the case. So I just refreshed the search thing, and then I got this answer. From the same thing, just within a few seconds later, you can even see the timestamp of the screen. It's like exactly within the same minute of it. Now, this is a kind of a situation where essentially the AI model, for whatever reason, it did some retrieval of the things, and it was summarizing the response. And in one case, it summarized it one way, and in another case, it summarized it in another way. Presumably because in the documents that it retrieved, there is some information indicating both types of things. So the broader picture question that comes up is increasingly, as more and more people are using LLMs as the front ends for their web search and retrieving information, how does the internal parametric knowledge of the model, which is in the neural network, impact its overall search responses? That's the question that we're interested in. What happens when retrieved results come from different sources where the information contained in them actually contradicts each other? And what happens if that knowledge actually contradicts its own parametric knowledge? How is all this fusion happening? And this is an example of a scenario where I think we have LLMs exhibiting some form of agency. And it is in this context, we had a hypothesis, which we called as the latent preference hypothesis. And it's a very simple hypothesis. At a very high level, our guess is that, and we're going to validate this through a series of experiments later that I'm going to describe, which is that LLMs today have parametric knowledge about the information sources. And what I mean by parametric knowledge about the information sources is they have some sort of a implicit notion of trust or page rank, if you will, based on the source from which the information is coming. And this knowledge actually manifests itself as some sort of a preference for information from certain sources over others. That is, our guess is that LLMs would preferentially trust information from some sources over others in a very predictable manner, because this is something that you can extract out of the language model and say, for example, that LLM will always pick a story from Spiegel over Bild. Let me talk, most of this talk will focus on this hypothesis, and this is from a recent paper that we published at ICLR, which talks about this. So this is actually work done with a number of my co-authors and colleagues and collaborators, who unfortunately I'm not going to have the time to introduce. But before I go into that, let me quickly give another example. Scenario where increasingly LLMs are acting with some form of agency, which is today we see LLMs are increasingly being augmented with tools and function calling abilities. Now, to explain what I mean by this tool or function calling, here is a simple plot where we looked at data we gathered from 300 users about their conversations with ChatGPT. So we had over 830,000 real conversations users had with ChatGPT, and we were looking at how many times the model answered using its own parametric knowledge versus in how many cases did it resort to calling some tool in the backend before it gave the final answer. So what this plot is showing is in November 2022, when ChatGPT originally started, the number of tool calls, in fact, tool calling was not even available. But today, fast forward to March 2026, almost 1 in 5 responses are aided by the model calling some external tool. And typically that thing is web search, but there are also increasingly an entire marketplace of these tools. If you have heard about something called MCP from Anthropic, the Model Context Protocols and MCP servers are nothing more than are offering tools that language models can call. And then in this context, we have another hypothesis, which we call as the latent perception hypothesis. And what we mean by this specifically is when a task is given to an LLM, like when a user types something in ChatGPT, the LLM is deciding whether or not it needs help with solving the task. And it's also deciding if it needs help, whether a particular tool that it is going to call will help it with answering it better. These are judgments that the language model has to make. But if you think about this, the information for this judgment doesn't exist in a very objective form. It's almost like you trying to decide when you need help with trying to solve a task and who might be the best person to ask for the help. And these are very difficult judgments in general. So our hypothesis is that LLM's perceptions of their need and utility of calling tools would actually differ from their true need and utility. And therefore, it will often result in these models overcalling or undercalling tools. That means they often call tools when they don't need them, and they will not call tools in scenarios where they do need them. I'm not going to talk too much about this, but just at a very high level, here is a table of the performance of different types of GPT, different types of open models, GPT, Quen, Gemma, Mistral, Llama. And what we're showing here is that the first thing with no tool is when the model tries to solve a particular task only by itself in a standalone fashion. And always tool is if we forced it to always call the tool, how would it perform? Versus optimal is what would have been the best case scenario if it only called the tools when it would actually need them. And the high order bit is calling tools does help improve performance. With tools, they do better. The score is like the quality of the response or the quality of performance in solving the task. But if you looked at the optimal versus always calling the tool, sometimes it's actually the optimal is like assuming some knowledge that the LLM does not have when it is running. This is something that we evaluated with some from an external perspective. So what it turns out is that the high order takeaway is that oftentimes you can actually do better by calling the tools fewer times. However, this optimal performance assumes an oracle that can precisely predict whether or not calling a tool would actually help the thing. In practice, you cannot design this oracle. You can try to mimic that oracle. But today, the self-decision by LLMs are far from mimicking these kinds of oracles. In fact, this is part of another submission paper that we're working on that is under submission. If you're interested in the details of this work, please feel free to look it up. And since we have a limited time, let me go back to this latent preference hypothesis and then show you some experimental results that would validate this hypothesis. Again, as a quick reminder, the basic hypothesis here is that language models have an implicit notion of trust in different sources of information. And whenever it gets a piece of information from a source that it trusts more, it will actually prefer that over other sources. It's almost like saying LLMs have an implicit page rank. Now, so the first, I want to describe this in very simple experiments rather than make it a bit more formal. You can read the paper to look at to understand a bit more formal setting that we have. So the experimental setup that we have is one of selecting news stories. So here we went to the site called allsites.com. So allsites.com is a website where every day they have all the major they cover the major events of the day around the world. But the interesting thing that they do is they have stories from right, left, and center leading news media sites about how they are covering a particular event. So for example, here they're talking about judge reordering Trump administration to rehire some employees that have been laid off. And then here if you look at the titles that are given by the right leaning versus left versus center, you'll start seeing that there is some stance that these articles are taking, even though they're talking about the exact same thing. So for example, from the left, it says, judge orders Trump to rehire things that were let go in mass firings, whereas the right says the judge orders Trump to rehire fired federal workers. So you can see the change in stance. In any case, so the setup was a very simple one. So we prompted the LLM by saying that, look, you're a seasoned and independent news editor. Your task is to select some articles that you would prefer to publish. And then what we do is tell it that a good article should be informative, should be unbiased, and so on. And then we say, here are some 3 articles from each of the 3 leanings. And then we say, pick one, right? Select one of them. So we just give the 3 articles, and then we ask it to pick one of them, and then we give a brief explanation for why you would select to publish one of the 3 articles over the others. And here, let me show you some quick results from experimenting with GPT-4o Mini before showing for all the other models. So in terms of source story selection, when we did this, what we found was that most of the time, the articles that were selected were either from the left-leaning news sources or the center-leaning news sources, rather than the right-leaning news sources. So there are very few stories from the right-leaning sources that were picked. Now, this could be for a variety of different reasons. It could be because of the content. It could be because of the style. And we don't yet know whether this is actually because of the source, right? Like the reputation that the source has. So what we did was to understand the impact of the source. One thing I should have mentioned is we give the entire text of the article, and each time we also mention the source. That is, this is where we would say this is New York Times or Wall Street Journal or whatever else. And so we want to understand to what extent the source name is impacting the selection of the article. So what we did was we decided to anonymize the source. What if we gave the exact same articles, text and everything, but we just removed the source, where we say source is unknown. then all of a sudden we see the selection of articles changing. All of a sudden there are more articles from the right-leaning side that are picked. This suggests some strong evidence for latent preferences for the sources of the information. And to further confirm this, what we did was a simple experiment where we swapped the sources. That means we showed the same articles, but then we switched the right-leaning and the left-leaning sources. So we posed as if the right-leaning article was written by New York Times and the left-leaning article was written by Wall Street Journal, say, for example. And then all of a sudden, when we swap the left and right, in fact, the choices also switch in a very predictable manner. And the same thing with center and right as well. So all these things, what they're showing is a strong evidence for latent preference for sources. It's the sources that is actually driving the selection, even more than the content of the articles themselves. Now, we also wanted to see whether because we asked it to explain its preferences, whether it in the explanations, would the model actually admit that it's being influenced by the source? Now, it turns out that explanations do really reveal some of these source preferences, but it's not all the time. It reveals around 40% of the time. And then we wanted to do another simple experiment where we said, okay, what if we tried to tell the LLM, don't be biased by your impressions about the sources, right? What if we explicitly instructed the LLM to not be swayed by your preconceived notions about certain news sources and focus solely on the quality of the article? What would happen? Like, can we actually debias it by giving it explicit instructions? And what happened when we did this was that the results didn't change in terms of the decisions of choice of the articles. But interestingly, in the explanations, it stopped referring to the source preferences. In other words, the final decisions it was making were exactly the same, but excepting that in this case, in the explanations, it would never mention that it was biased by the source. So it's sort of like implicitly lying rather than changing the final decision. So in other words, implicit bias training is not as straightforward as changing a prompt in these kinds of things. Now, we also did some extensive experiments across different models, GPT, Llama, Qwen, Phi, and Mistral. And one of the interesting things that we found was that most models do show strong preferences. I'm not expecting to go through all these pictures here. I'm sorry for this being so information dense. But the interesting thing is the smaller models consistently exhibit weaker preferences. So when we compared Llama 1 billion with 8 billion, and Qwen 1 billion with 7 billion, and Phi Mini with Phi 4, which is a bigger model, the bigger models always have stronger source preferences, whereas the weaker models are seemingly indifferent to the sources. That means they don't seem to have as much picked up as much preferences for certain sources of information over others. Now, in the interest of time, I'm going to skip over some additional experiments we did where we tried to avoid confounders by actually generating synthetic news articles synthetic news articles so that we have the same content that is written in slightly different styles, but which we assign then to various different news media platforms to see in other words, to sort of extract what sort of preferences, which media sources are more preferred than others. So in the process, you can actually come up with a ranking or a page rank, implicit page rank that, or the implicit trust rank that the model has for various different news sources. So here, for example, what this picture is showing is that Qwen actually more or less prefers all media sources similarly. So in terms of the win percentages for the competitions that we conducted, when you say that a news source is an article is from one source versus another, it's somewhat equal for Qwen 1.5 billion, but then GPT-4o Mini, you see a clear preference towards certain sources than others. And these sources include those from the US, China, and Europe as well. So you can kind of extract these sorts of things from the different models. So I'm going to skip over, but in the paper we show whether these things are correlated with geographies and models. That means are the models from China or models from Europe preferring European sources or Chinese sources more than the US in terms of their trust. The high order bit is surprisingly, perhaps, they don't show, all of them are more or less all of them have similar rankings or similar sorts of rankings for trust in the news sources, and they actually don't vary that much based on the place or the location of the developers of these models. So I'm going to skip over some more things about how good they are at recognizing expertise. That is whether when the topic where the information has to be selected from changes from, say, some broader news information about general news to being very specific about, say, for example, articles related to research in different domains like computational linguistics versus computer vision versus health and medicine versus math and physics. In these situations, we also try to see whether the models would prefer actually papers or information from information that is published in venues that are more highly reputed, like journals or conferences that are more highly reputed for those particular topics. And it actually turns out that these models have a very good sense of which venues are more prestigious or more reputed for these different domains. So, for example, when we asked it to pick some papers to recommend for a university level seminar courses, what we found was that when it came to computational linguistics, it was preferring papers that were published at ACL and EMNLP, whereas when you change it to computer vision and pattern recognition seminar, it was picking papers from CVPR and ICCV and so on. And notice that in this particular experiment, we were keeping the articles the same. We were playing this game of asking it to pick from a selected set of articles. The game that we were playing was we were just changing the place or the venue where we were claiming that these articles were published. So in other words, source preferences actually vary based on domain expertise. So to conclude, there are a number of open questions that we can discuss, which is how do these latent preferences emerge, particularly during pre-training and fine-tuning? That's an interesting question to think through. And there is a question of should we be engineering LLMs to prefer some sources, or is the right thing to do to be neutral to all sources? This is again a policy question as well, because it's not clear that it's a bad thing if LLMs actually preferred some sources of information over others. But then we need to be aware of the biases they introduce down the road. And then there is this bigger picture, broader question of how do we enable trustworthy and unbiased generative AI search if that's the direction in which the world is headed. And here we may have to think through the fact that the cognitive biases of the humans and the LLMs may be different. And there is a question of like what sort of trust in sources should the LLMs actually learn to have, and should it be the same as what humans have? Should it be personalized? And all these other questions come up. So with that, I'm going to stop and take any questions that you have.
Thank you so much, Krishna. This was a very, very interesting talk. And I see there is one question, but before moving to the question, I have a really, probably other people have asked you, but why didn't you include Grok in your study?
Yes. So we are actually doing that going forward. At the time when we did this, we didn't include, we didn't think that Grok was a major one, but I hear what you're saying.
Yeah.
We are doing some work in terms of looking at the conversations people are having on various different conversational AI platforms. So we're taking this approach of asking people to donate their chat data. And there we find that we do see striking differences between how people are interacting with Grok versus other conversational AI platforms.
Yeah, like on the jailbreak project that I presented, it was an outlier. In many fronts, it's an outlier. That's why I think it could be very interesting to possibly corroborate or not some potential hypotheses as to why these preferences, are emerging. Alan Smeaton has a question. It says the New York Times published an article last month where the accuracy of Google's AI overviews was analyzed using simple Q&A. And the underlying models were earlier versions of Gemini, but even with Gemini 3, the AI overviews were accurate 91% of the time, or put another way, they were incorrect 9% of the time. This means that the AI overviews have tens of millions of wrong answers every hour. And you had an example, right, in your example about the Berlin.
Yes.
So how do such fundamental inaccuracies in underlying FMs impact your work and your results?
So I think this is a very this is a bit of a high level question in the sense of this is what I've been pondering ever since I got this. In fact, I will admit that this response made me wonder, like, about this sort of a question. Like, increasingly, if I notice that, even I don't know if this is a more broader phenomena, but I at least start these days, whenever I do search, I start paying a lot of attention to the AI overview, which is summarizing the results of the search, right? As opposed to actually browsing the links myself. In the process, there is a chance that we are being misled because we are relying on the LLM to summarize the information from us, right? So this actually poses, this actually feels like a very important problem that needs to be studied more. And that's all I'm afraid I can say at this point. I personally wish that there were that this is something that more people looked at, because I believe that many, or I have a feeling that today there is an assumption being made when LLMs are being deployed as front ends, that the tools or the web search responses will somehow all be good or correct. And therefore, all that the model needs to do is summarize them, right? But the top K search results can have very different, can sometimes make very different points, particularly when you're doing search for medical information or something like that, right? You could have a top search result that contradicts the information given in the second ranked search result. In those cases, how should the LLM summarize this information?
Yeah, I mean, something else that I have observed, I actually don't actually trust any of these AI summaries myself. And something that I have observed too is that they're very context dependent. Like if you're in different locations, you can get different answers. Even when the context shouldn't matter, for questions that are really not about locations of things, where, it could matter where you are. So I do, and I think your history is used if you're locked in versus in a private mode. Like, I think there is a lot of factors that play a role in reweighting, the information to decide what to include in the summaries. And I think it's completely obscure right now as how these summaries are created. So I don't think it's even necessarily a summary of the top search results. I think there are other factors that are taken into account on top of that.
Yes. Yes. I noticed another.
There's another comment. There's another question. Agreed, Nuria. Thank you, Alan.
Yes. I can also answer very quickly this question. Doesn't it read tools metadata to preferred tools?
Sorry. Oh, I didn't see it. Yeah,
no worries.
Sorry.
This is actually a very fascinating question. So at a high level, there is a thing of like, how does it, when this is about this latent, I guess what I was calling as a perception hypothesis, which is when an LLM is deciding which tool to use, how is it making that decision? Yes, it will be influenced by the tool metadata. That is, what is, for those who are not familiar, whenever you're trying to connect an LLM to an external tool, what you do is you describe how to call the tool, right? There is a description of the tool, which is about how to invoke the tool. But there is also some additional information that describes when to call the tool, or in what situations the tool might be helpful, right? As you can imagine, this is a very difficult thing to communicate in just a few sentences to the LLM when the tool is reliable versus not reliable, especially for the hundreds of thousands of tools that you have there, right? So, for example, just for web search, there is Google based SERP, tool. There is Stabili, there is Brave Search, there is Perplexity. There's lots of web search tools. How should a model know which web search tool to use today? Now, today, the LLMs just get a description from the tool developers themselves. What if the tool developer said, this is a phenomenal 100% accurate tool? Today, we just pass it on to the LLM, which is, if you think about it, kind of ridiculous. Like, shouldn't there be like I mean, this is all part of the tool harness, right? As people call it. So this is what I mean by saying the harness is the thing that gives agency to these AI models. This is the part of the architecture of deployment for the AI models. And this is where I feel there is a lot more attention that needs to be paid than what is being paid today, because that essentially ends up determining what happens.
Yeah, very good. Unfortunately, I think we are now out of time. So thank you so much, Krishna, for a wonderful and really stimulating presentation. And I think we can move on to the next speaker. And by the way, Krishna, just as a reminder, we have the Human-Centric Machine Learning workshop next week in case you can make it. Okay, wonderful.
I will attend online for some parts of it.
Okay,
looking forward to it.
Thank you. Thank you so much. Thank you.
So next, thank you very much, Krishna. It was fantastic. Thank you. Fantastic talk. And next, I would like to invite again Tatiana Zakharchenko, who is one of the workshop co-organizers and founding director of the new Center for Data, AI and Society at the Ukrainian Catholic University. She will tell us about it later, but she will now introduce the speaker. Tatiana, please introduce the next speaker. Thank you.
Yeah, thank you. Thank you. So I'm happy to introduce our next speaker, Lesia Semenova. She is the assistant professor of computer science at Rutgers University in the United States, where she leads a research group on safe, trustworthy, and interpretable AI. Before joining Rutgers, Lesia was a postdoctoral researcher at Microsoft Research in New York, and she received her PhD in computer science from Duke University. Her work contributes to the foundation of interpretable machine learning and develops methods that use model multiplicity to support robustness and safer decision-making in high-stakes domains, including healthcare and public policy. She will speak about from model uncertainty to trust, safe and interpretable AI under the Rashomon effect. So Lesia, the floor is yours.
Thank you so much, Tatiana, for introduction. And thank you everyone for the amazing workshop. I have been enjoying all of the talks. I will share my screen. Okay, great. So at Rutgers, I lead Trace AI Lab, and we study transparency of AI and ML models. And today I would like to talk about safety through personalization. And essentially, when I think about questions that are interesting to asking, one of them is like, how do we make AI systems that we can truly understand, trust, and rely on? And when we ask this question, when you think about this alignment, we often mean aligning AI with human values. So, and overall, huge teams of researchers and engineering are working right now to make sure that these models are less harmful, for example, by filtering toxic comments or like more neutral to counter some biases in online data. And these are like some behavioral safeguards that we like all want models to have, hopefully by default. But there is another like deeper level of that alignment, which is user intent. And that part is way less understood. And that's where things get interesting because it's extremely contextual. So it depends what user wants, what they do not want, what they believe the model should understand about them. And one side of my work focuses on how we can make these AI models not only safer in general, but also responding to the intent. By studying diversity of different passes that AI system or ML model can take to achieve some specific goal. And in reality, very rarely there is one single golden answer. Very often we just have many different perspectives to solve the same problem. For example, let's say that we just want to understand which number is this, and we already can have a different perspective given how we look at it from one side or another one, and we can have multiple answers. And this is known as a Rashomon effect. Essentially, it's like when we can have the same view on the data, on the same evidence, but may have different explanation to it. And Rashomon effect occurs when we have the same data supporting the different phenomena. And very interesting question is then, because like very often we have been taught to optimize for one single model, is then which model should I actually choose? And today I would like to talk about if you have that desired data in mind. So let's say that we want to optimize for interpretability, fairness, robustness, or privacy. In other words, caring about properties that we should care about when we deploy our models in real world. Then this existence of many good models actually allows us for personalized model selection. And let me give you an example of that. I've been working with a team of doctors, and we've been trying to study the epilepsy. And it occurs for a lot of people. It occurs around for 50 million people worldwide. And essentially, we have no idea why it's actually occurring. We know that we can detect some EEG recording and try to detect spikes. And still like studying where the spike occurs, how to acknowledge it, how to try to find that proof for that is very important, especially for people who are having seizures. And the data that we have been provided by the doctors have been quite interesting. So they had one-dimensional recordings with a goal to do final classification alongside the probability of having that spike. So right now on the screen from the left to right, you can see like the almost like a probability of having that spike, where the leftmost model is the one that most likely don't have any spikes, and the rightmost model are the ones that are having spikes. And essentially our goal was to try to look for these discharges, these changes in data, where I would like say, okay, this may not have a spike and this might have a spike. And because we were working with this team of doctors, we had a very highly trained domain experts on the team. So we wanted to try and design something a little bit better than a black box model. So we look into interpretable modeling, and we ask a question of the form, can we design a model that has some inherently interpretable reasoning towards how it's making its decision? In other words, we looked into proto-PNets, or models that perform this looks like that reasoning in the following form. Give it some input, and here I have different channels like that are meaningful for EEG recording. So given some input, I want to find best matches in my data sets that have occurred before me, so that I can say, I have classified this input as having a seizure because I saw another inputs in my data, and I definitely know that they are having a seizure based on what my domain experts have provided me as labels that they have given to me. So this allows for any classifications that I'm making to have some proof towards it, because now we know how the model makes a decision and what it relies on. And just to give you a little bit of understanding to uncover that, how we uncovered that black box, we had the following structure. So, and we call this proto-EEG Canaan architecture. So essentially we had some input, and then we took as a backbone-based best model in the class, which in that time was SpikeNet model, and it was achieving like around 80% accuracy. And then we computed our EEG embedding. So that would be like the standard black box performance. But then we added something new, which is global comparison layer. It essentially computes the similarity between embedding and each sample in the training set. And we compute the similarity by multiplying each channel overall similarity and channel-wise weight. So, and we also added some interpretable features to this data just to help the model to understand the signal better, such as a range, variance, and some signal frequencies coming from Fourier transform from the input. And then we were able to finally compute some predictions, which is the average label for top k most similar neighbors, and we use k equal to 10. So now equipped with this model, we're able to do this interpretable reasoning and have a very simple answers. So this input looks like those inputs, and that's why we have classified it as having a spike. And further, we could study by channels and visualize a top plot where in the brain it could possibly occur, which was very interesting for our doctors as it aligned with some type of their domain knowledge. So this kind of like process shows us that even given some medical data, we can design interpretable models to help doctors understand the data and analyze them. But a way more interesting process has been happening on the back end, on the engineering process of designing this whole methodology that took us approximately 2 years. And it was like this. So we started with the first model. As I mentioned, it was a SpikeNet model, and it was around 80% accurate. So, and we said, okay, now we're going to try our interpretable model. So we tried ProtoPNet, we got our second model, it beat baseline, it was 80% accurate. We went to our doctors. We said, here is a great model. It's interpretable. It performs as good as the best model in class that you had. And they said, we have no idea what it's doing. We just don't understand it. It aligns matches that are not like useful for us. It's not how we make decisions. So we said, okay, can you please educate us? How do you make a decision? Like what should be important for making this EEG prediction? And as we went through this process, we realized why doctors spend a lot of time in training, because it's a very complex process. You don't only analyze the spikes, the foreground information, but also the background information. And also some doctors disagree on a very important corner cases. So as you notice, our performance is around 80, and this is the best that we can get. So it's not 100. There is some inherent noise to our data. So, but we kept trying. So we tried another model, and we went overall through like a couple of iterations, around 10 or so. And finally, our doctors told us, okay, we like this model. It more or less corresponds to how we would make a decision. It is interesting. Let's try to test it on like the domain experts. So we had a human study, and indeed that model was doing quite well. And if I would map this whole process into the hypothesis space, so let's say I have a whole space of models, and then I had that baseline model, which would be SpikeNet. And now I'm going through how I'm making my decisions, mapping one model, another one. They all have been accurate and all had very different properties. From some model that was completely black box to some models that was completely interpretable and aligned with our domain experts. So I call this set of near optimal models that have the same performance a Rashomon set. Essentially, it's as if I take my baseline model, which was SpikeNet, and look at its performance, either measured in terms of true and empirical risk, typically empirical, since it's what we have access to, and then look at the performance of all models that are below a threshold that was defined by this best model in class, and some parameter, which I would call Rashomon parameter. And it doesn't have to be anything large. It could be 0% or 1% of the loss, but essentially it determines how much we are willing to sacrifice for some model diversity. And these two quantities, the performance of best model in class and Rashomon parameter, determines a threshold that I will look under and consider all possible models that will form this Rashomon set. So now if you remember our goal in mind, where we said, oh, can we actually choose models that align with some different properties that we desire? So now we know that like unwillingly going through this spike detection process, we explored the Rashomon set. And we were able to find a good interpretable models that aligned with our needs. So the key takeaway of today's talk would be the following. If we have large Rashomon set, which is a set of near optimal models, we can simply search for the desirable property. Now, interestingly, if our property changes, we can search for it again. And I would like to pause here for a second, because I think the existence of this large Rashomon set, it changes a lot how we approach optimization in ML and AI. We used to optimize for one single model. And what this whole process is telling us is that very often, especially for high-stakes decision domains, especially when you have some inherent noise present, there is no one single model. There are multiple of them. So maybe optimizing for that set of models can give you better results towards the end, especially if you know that some different properties would be desired and studied in the future. Okay, so I've been using this word Rashomon, and I would like to give you a little bit of backstory about it. So it takes its way from Akira Kurosawa movie, and it's 1950 film, and it occurred around 4 characters. And then later they were asked, they all relived the same tragic event. And then later in court were asked what happened. And they gave very, very different, even contradictory statements. And later in 2001, Leo Brayman was playing with linear models. And he noticed that very often you can have the same linear model with exactly the same performance, but relying on very different coefficients. And we know that those are associated with feature importance. So essentially, by relying on different coefficients, they mean that they highlight different properties, different feature importance of the data. So, and that's how he introduced Rashomon effect into machine learning, saying that what I call the Rashomon effect is where often there is a multiple explanations in the same functional class for the same minimum error rate. And in fact, in my research across different domains, I notice it everywhere. So for example, for tabular data, there have been explainable challenge in explainable AI FICO challenge. And the dataset was given that tries to predict trustworthiness of the credit of the users. And here is a visualization of different methods with different complexities from different hypothesis spaces in terms of test accuracy and test AUC performing on the same dataset. And you can see here we have all possible variety of models, from something like simple linear model, like logistic regression, to more complex 8-layer neural networks, to some interpretable models such as 2-layer additive risk models. So we're all interpretable models are in blue and black box are in orange. And you can see that all of them have similar test accuracy and test AUC as well, basically meaning that performance are equal and all of these models belong to the Rashomon set. Similarly, we can observe in language. So for example, if our prompt is underspecified, let's say ask a question, how many restaurants are on the main street? There are so many answers to it. Main street in which city? Or like which restaurant are you specifically looking for? So legitimately for my epistemic uncertainty prompt, there could be a lot of different answers to it. Or even if I don't have any underspecifications, there could be representation ambiguity. So for example, it has been shown that you can take BERT models and just by changing the random seed, you can have very different performance of those, where one would actually learn some robust like language rules, and the other one will rely on spurious correlations. Then interesting question is like, why does this effect occur? And one was a reason we already explored right here, which is underspecification. Maybe I didn't specify my problem enough. I chose wrong hypothesis space. I didn't train enough. Maybe I didn't design good constraints. So naturally there could be that model uncertainty. But the more interesting use cases are the ones that come directly from the data, especially human data, high stakes decision data. Because everything about us as humans is tied to randomness in the world. Things can change. We can lose job, get job, gain weight, lose weight, change our diets. And all of this can influence into how predictions about us are being made. So we make a direct connection between noise in our data generation processes, noise in high stakes decision domains, to a simplicity of the models and to existence of the Rashomon effect. There could also be inherent diversity in our data problem solution. So for example, if I'm solving a math problem, there could be legitimately multiple ways that are 100% accurate, so there is no noise, to achieve the same answer. A very simple example to see that is another type of interpretable neural networks, which are concept bottleneck models. And instead of relying on some inputs on some samples from my training data, they actually predict human understandable concepts, whereas these concepts could be predefined or discovered. And here I'm showing the result from one of the methods that we have developed to help to compute the Rashomon set of these concept bottleneck models. And you can see that given a class of tiger, so let's say we want to understand which model, why the model predicted this specific image as class tiger, we can see that the model rely on different reasoning. So for example, one model can look into some properties such as being strong, but another model can look into the color of the tiger, such as being orange. And another model can look at the speed, which is being fast. And they can also utilize some negative information. Like for example, the tigers do not swim. Well, maybe they do, but at least not to predicting the tiger as it is, or some things that as they don't have a long neck. So essentially, this gives us different ways in which models can predict the same class from different perspectives. And then as a domain experts of people who know what we want to model properties to have or not to have, we can select the one that we will like the most to be deployed. And this Rashomon CBMs is one example how we can compute Rashomon set. It relies on optimizing diversity loss, which we define based on cosine similarity, and also LoRa adapters. But there are way more methods that right now allow us to compute Rashomon set. Even something simple as unstructural exploration, as we had in the epilepsy example, can help. Simply by changing the random seed, we can already sample models from the Rashomon set. Very often we do it during hyperparameter tuning. When we do some sweep of the hyperparameters, we would actually check our performance, we already would form Rashomon set. However, there are methods that allowed more structural exploration, such as prototypical neural networks. So that's the one that we studied in the epilepsy example. There is a method that explicitly allows to study Rashomon set of prototypical neural nets. Or there are methods for more simpler hypothesis spaces, such as trees or generalized additive models. And specifically for sparse trees, these methods are very interesting because they allow us to compute the Rashomon set exactly. So we know that all of the models that we have computed exactly belong to the Rashomon set. None are excluded, none are that should not be there. It's like we can compute it as it is. And interestingly, having these methods can help us study multiple properties of the Rashomon sets or prove or disprove our points. So for example, one of the things that we considered is trying to benchmark Rashomon sets on these properties that such as robustness. Let's say we want to understand how robust is model to some adversarial attacks, or stability, how stable it is to noise. How private it is if somebody would do membership inference attack, as if trying to inquire if the given example can be part of your training data given your model only. Or fairness, where we want so there would not be disparities between different groups. And having this algorithm for computing the Rashomon set of trees, which is exact, we said, okay, let me try to take all of the methods that optimize for this desired data directly. So I know that their objective would be optimizing accuracy subject to these desired data constraints. But now I'm going to compute my Rashomon set based on accuracy only. And then I will compare, does that Rashomon set maybe already contains model that are close in performance on these desired data properties? And turns out it does. So here is a visualization of based on benchmark German credit data set, where on x-axis I have fairness, which is a disparity, and on y-axis I have accuracy, and in both cases higher is better. Now blue blob describes my Rashomon set, so each dot is essentially a model in the Rashomon set, and we show here accuracy and fairness, and each of the colorful dot describes my different methods. So, and these methods are optimal tree methods that have been optimized for accuracy and fairness simultaneously. And you can see that for each of the method performance, we can find similar model, and it may not be the same, right? But we can find a model with similar performance in this Rashomon set, essentially telling me that we can explicitly optimize for trustworthiness. So what does it mean for the bigger picture? Let's say I have my Rashomon set, and we already know there are methods to compute models from it. So if I have some predefined properties such as robust models, I can find it there. Or fair models, I can still find it there. Interpretable models or privacy-preserving models, which leads us to our takeaway. If we have a large Rashomon set, we can simply search for the desirable property and say it changes. So maybe we decided to be interpretable and private. We can search for it again. So this leads to this interesting conclusion where I do think that the uncertainty itself, the Rashomon set itself, should be a policy object. And it's essentially important because some of these properties can have trade-offs. For example, if I would consider robustness and privacy, especially privacy as if releasing some information leak around my data set, these properties can be trade-off given the Rashomon set. More specifically, the more models I disclose, so the more models I would change in the production by taking from the set of near optimal models, the more information I leak to the adversary so they can design a better attack against my data, against my system. And essentially studying these all properties in unifying form is very important. Besides trying to study each property in isolation, using the Rashomon set, we can also build an argument that shows why simple interpretable models should be the default. Essentially, the argument is like this, which is summarized in these papers. Very often, as we mentioned, the high decision domains data are very noisy. And that noise is one of the reasons why we will automatically regularize more on the noisy data. So essentially, noise acts as an implicit regularizer that leads us to simpler models within the Rashomon set. Or even if we don't have Rashomon set exactly, so let's say there was some interesting domain where we couldn't compute it exactly, we can still approximate it and use it to design a better multiplicity of our algorithms. And we did so for explainable AI. And this is part of the work with students from Ukraine, from Kanu and Uku, that was accepted to NeurIPS last year. So essentially, we approximated the Rashomon set and were able to design better explainability, more robust algorithms. So taking it all together, I would like you to leave with 3 takeaways that help us transform this source of uncertainty, which it is, to foundation for trust, which we can essentially select models for our personalized goals. First, if you have large Rashomon set, we can search for desirable property. Second, if you work in high-stakes decision domains, think about interpretable models first. We do have a formal proof that says if you expect larger Rashomon sets, those interpretable models will exist in it. And third, we can use that multiplicity of our knowledge to design a better algorithms for our trustworthy decision-making. And there are a lot of future directions. I truly believe that we should keep building uncertainty-aware Rashomon set pipelines and algorithms. And some of the open directions include the causes of the Rashomon set. We talked about noise, we talked about underspecification, but there could be so much more reasons why it occurs. Maybe it comes from feature redundancy or collinearity. There could be more studies on different types of noise. How do we find or represent Rashomon sets at scale? It only occurs in vision language model and large language models, and not only at the model size. It's a multiplicity of representation and multiplicities that can occur within different layers as well. Then how do we display these Rashomon sets for human model interactions? So what I didn't mention is that sometimes for some benchmark data sets, the size of the Rashomon set can get up to millions of models or even 1 billion of models. It's a lot of models to choose from. So we do need more interactive frameworks to help humans to interact with this huge set of models. And finally, how do we address some individual arbitrariness in the deployment? So imagine having 1 billion of models, and then it affects somebody's life. And now we know that this model will, of course, disagree on prediction for some personal, let's say, me applying for credit. So different models will disagree. And then it creates an issue as if I applied for credit and I know I'm denied by one model, I could be approved by another model. So this individual arbitrariness should be resolved in deployment as well. So thank you for your attention, and hopefully we can all, as next time as you optimize for some property, think about multiplicity and some desired data as well.
Thank you, Lesia. So interesting, really. Thank you so much.
Thank you.
So yeah, we have actually 2 questions from Manir Gersala. So I guess I will ask you the first one and then move to the next, okay? So when the medical doctor said about the TENS model, you know what? We like this model. Do you have any metric to assess the likability of ML model to the decision makers? I mean, either that is in human study, something like ML model quality of experience assessment approach, or especially since there are still black box are not fully explainable. So that's the first question.
Thank you so much for asking it. This is an excellent question. A very short answer is that I do not have a very principled answer to this. This is a very complicated question. But one possible way could be task-dependent performance. So in our specific case, epilepsy is a complex problem. So even though we ask doctors, can you please teach us how do you make these decisions? We couldn't fully understand it, even like this, like a 30-minute description, which means that it's a way more complex something to be taught than we could just do. But they, for example, told us, background information and foreground information are both important. So that helped us to guide intuition further into model development. So one way to assess likability could be a very specific task-grounded metric. So for example, let's say, does this model take into account both foreground and background? Or does the signal between channels is very different compared to some specific measurement? So essentially, even though it's hard to assess it in the big picture, we could still design some simple task-dependent evaluations to help us in that sense, and indeed reduce the number of iterations that we went through.
Right, and another continuation of the previous, do you also consider the observer effect in the Rashomon effect, where the fact of thinking about the object in human studies alters the human feedback outcome? These are my questions about bias and trust under human-centric AI decision-making under uncertainty. Thank you.
Thank you. This is a really great question. So actually, this would be a really great, future studies type of work. Here is why. Typically, when we compute Rashomon set, we don't have human involved. So we compute it based on the data that we have. And only after we computed it, we add human to the picture. And then we say, okay, here is a multiplicity of models. What would you like? But I think what you're asking is way more interesting. What if the human knew from the beginning there is a Rashomon set? So I think that will help us to guide maybe to better summaries or better finding subset of the Rashomon set more aligned with human goals to begin with, which is very interesting, but I don't think it has been done yet, which could be a great future work.
Thank you so much again for joining and for everything that you already done for Ukraine too.
Thank you. It was my pleasure to be here today. Thank you for the invitation.
Thank you very much. Fantastic talk. So thank you very much. So the next we have two shorter talks, and I'll let Rostislav please to introduce the speakers. Thank you.
Thank you, Joseph. And now I have a great pleasure of introducing the next speaker. And the next speaker is Valentyn Melnychuk. Valentyn is a PhD candidate at the Institute of AI in Management at the Ludwig Maximilian University of Munich. Valentyn's research lies at the intersection of causal machine learning, treatment effect estimation, and probabilistic modeling. All of these things are very closely related to our today's topics. So his work is particularly vital to today's theme, just because he doesn't just focus on model performance. He investigates the core of reliability, fairness, and safety in AI systems. So today, Valentyn will share his insights on a very interesting topic of causal machine learning under privacy constraints. And Valentyn, the floor is yours. Welcome.
Oh, yeah. Thank you, Rostislav. I hope you can hear me well. Okay, great. Thank you for invitation. I'm really flattered to be able to talk about the research in our group. My name is Valentyn, and I am about to finish my PhD at the LMU Munich. And here today I want to talk about one of our latest papers. Yeah, this work was done. I'm actually a second author. The first author, Maresa, she couldn't join today, unfortunately, but she kind of provided the presentation, and it was a pleasure to work with her, and also Professor Feurigl. And basically, what I would discuss today would be our iClear 2025 paper called Differentially Private Learners for Heterogeneous Treatment Effects. And to start with basically the motivation for the project. The project itself kind of combines two areas of reliable or safe machine learning. So causal machine learning on itself already kind of formalizes the idea of decision making, or how can we make better treatments, better individualized treatments, or it tries to estimate the treatment effects from data in a very reliable and formal way. And privacy itself also allows us to kind of share the data sets. It allows us to share certain statistics of the data sets in a way that we cannot identify anyone's identity. And consider the following problem that we have. We have a patient data which we want to use for heterogeneous treatment effect estimation, so that we can understand what drugs are effective for what parts of population. So here, for example, we know that heterogeneous treatment effects really allow to say, for example, for old people, some treatment might be more effective. For younger generation, it might be basically even detrimental. So kind of allows us to go beyond the averages and say like, oh, for specifically for me, whether certain medication would be effective. And recently, there is a whole bunch of causal machine learning methods developed specifically to kind of target the heterogeneous treatment effects. And they all sort of would rely on these large data sets, which are observational, and they come from electronic health records, for example. And those electronic health records, they contain multiple of like a lot of private data, for example, some clinical measurements, diagnoses, what sort of medications were administered, etc. And essentially, we face a problem that it's a very sensitive data that we use, and in many countries, I mean, also in European Union, there are a lot of regulations that basically oblige us to care about privacy or to enforce the strong privacy guarantees. Why do we want to use the differential privacy specifically? I mean, in principle, there are way simpler approaches. For example, you can have pseudonymization. So, for example, you just remove some direct identifiers like names or IDs from the data set, or you just change them with some random tokens. However, this approach is prone to, it's not super stable. So by just using other features like zip code, or like the combination of zip code and date of birth, we can already kind of match this medical data with some other data set, and then we can de-identify people. We can also try to mask. For example, we just throw away those columns, for example, date of birth. However, in this way, we kind of remove the useful information, so we wouldn't be able to have this treatment effect prediction, which also kind of considers the age. So, and again, there is no formal guarantee that it wouldn't be possible to de-identify people. And the same also holds for more formal definitions of anonymization, for example, k-anonymity. In this case, we would kind of try to change the data so that we wouldn't be able to distinguish any person from k-1 other units in the database. However, this approach is also prone to the attacks, and it's quite hard to implement for high-dimensional data. Therefore, in our work, we considered the concept of differential privacy. So I think it's around 20 years old, and it was proposed as a formal way to kind of release some summaries or some descriptions of the data set without actually revealing anyone's private information. So specifically here, I mean that if we want to build the epsilon delta differential private algorithm or mechanism or summary, we essentially perturb our mechanism in such a way that for every two neighboring data sets, D and D prime, neighboring means that they differ only in one patient, for example, or one unit of measurement. It's like the outputs of those mechanisms or summaries differ only with very small probability. And here epsilon denotes the privacy budget, and we also allow for some delta, which is called failure probability. And essentially that differential privacy ensures that whatever algorithm that we run on one data set, its output is almost indistinguishable from the same algorithm being run on the dataset D prime with a certain probability. And also in the original paper on the differential privacy, one of the simplest ways to ensure it was it's called the output perturbation. So essentially, whenever we have some algorithm or some machine learning algorithm, or even if we calculate some statistics like average of all the ages or average over some other column, we perturb this the estimated average with the Gaussian noise, and the Gaussian noise essentially considers what's the so-called delta, so it's L2 sensitivity. So it says what's the worst possible difference between those two mechanisms, and then it kind of considers this L2 sensitivity and adds the noise proportional to that sensitivity. So essentially, if there is a way to spill this private information, the Gaussian noise perturbation essentially kind of overrides it with noise. And the fundamental problem here is that this sensitivity, L2 sensitivity, is in general very hard to get, and we will talk about it further in the presentation. And just gonna give a quick background on the efficient estimation of conditional average treatment effects, or as I mentioned before, heterogeneous treatment effects. What we face is we have this sort of unusual regression problem. So we have a data set where we have confounders, we have a binary treatment, and we have some sort of outcome of interest. And we want to essentially estimate the treatment effect of A on Y. But we want to not just get a specific number, we want to build a regression function. So we say conditionally on the covariates X, what would be the effect? And for that, we use the useful definitions of other regressions. For example, we will later use the propensity score, so the probability of getting treatment, and the outcome functions, so the conditional expectation of the outcome given X and given A. And what we want to learn or estimate is the conditional average treatment effect. So the difference of potential outcome given treatment minus potential outcome without the treatment, conditional on the specific patient covariates. And in general, it's because for every patient, we only observe one outcome, but not the other one, not the counterfactual outcome. In general, this is impossible to learn. So we actually need to make the causal assumption, for example, that the X is a set of all the confounders and there are no other confounders. And under those assumptions, we essentially can reduce it to the difference in the conditional like outcome functions or conditional mean of the outcome. And a very standard way to build models for gait estimation is so-called two-stage meta-learners. The way they proceed is that they first fit the nuisance functions, and then they essentially, with any model of choice, that's why they're called meta-learners, and then you fix them. And at the second stage, we fit the target model that serves as the estimator of our gait. And what we want to do in our project, essentially, we want to provide the private predictor of gait. Yeah, in a also model agnostic way, so that we don't develop a specific privacy, like the privacy guarantees for a specific machine learning model, but for general class of any possible regression or classification. I mean, in our case, it's a regression. And here is, I'm just going to quickly go through the numer orthogonality and numer orthogonal meta-learners. So if we want to learn Kate, we essentially need to use the nuisance functions, because, as I said, we do not, for every single patient, we only observe one outcome, but not the other. So we need to do imputations. And in general, we can formulate the fitting model for Kate as the regression of mu1 minus mu0. And then we regress our second stage model on this difference. And then we can also apply some weights. And usually, if we would just do the blind, we would blindly plug in mu0, mu1, we would have too much error coming from the first stage of estimation. So there is a whole theory, essentially, that we can additionally use the propensity score, and then we can kind of remove the first order bias coming from this estimators of outcome functions. And the specific formulas are a little bit threatening, but essentially what the orthogonalization of the numer orthogonal of the Kate meta-learners mean is that we essentially now regress the second stage model on some pseudo outcome, which is comprised of again, it's a difference mu1 minus mu0, but now we have a special debiasing factor, which kind of removed this first order error. And it also depends on the propensity scores. And there are different examples. For example, there is a DR learner, which does no weighting, and then it kind of has high variance because we divide by propensity score. There is also R learner, where we learn Kate only in overlapping parts of the population. If anyone has a questions, I'll be happy to talk after our talk. But what we did in our paper, essentially, we extended the traditional Kate meta-learners so that they can be proven to be differentially private. So in our paper, we first fit, again, separately fit the private estimators of the nuisance functions. And then given those, we want to essentially release the model predictions for the second stage model. However, to privatize them, we need to add this sort of noise mechanism. We need to add a certain amount of noise. And in this case, we also consider the Gaussian noise mechanisms. And the only remaining problem is that to release the function, we, like all this differentially private theory works well for finite dimensional outputs. But because we want to release the full function, we have to apply some tricks. And in our case, we came up with two practical solutions. So the first one, we might just want to release the fixed number of queries. We say, like, for this specific subpopulations, we release the Kate, and then we never touch the original model anymore. Or there is also some works done for functional queries, but then we have to fit specific models, for example, at the second stage, for example, Gaussian processes. And essentially in our work, in the case one, we came up with a couple of new propositions. So in order for the finite amount of queries, we used the nice theory to kind of get this L2 sensitivity. We saw that it could be upper bounded by the gross error sensitivity, which actually consider it's like an influence function depending on this whole second stage estimation procedure. And yeah, there are a lot of math here, but essentially what we came up with is this sort of the scalar of the noise, which we need to add to kind of preserve the privacy. And we proved that even if when we add this noise, we do not the properties of Newman orthogonality and quasi-occurrential efficiency, they remain. So as in like, it's still possible to do some sort of consistent estimation. And the noise that we add is this small o of 1 divided by n. It kind of scales. It goes to 0 as we increase the dataset size. And in the second case, we considered, we kind of developed a specific way to fit the Gaussian processes. So at the end, we essentially add a zero-centered Gaussian process, which is again scaled with respect to with respect to how varying is this second stage pseudo outcome. Yeah, and so essentially, our project is again, it kind of showed how that achieving differential privacy in kind of complicated setting of treatment effect estimation is very non-trivial, and yeah, in my opinion, there has to be more research done on that. Yeah, if you want to actually like publicly release some Kate models in a private way. Yeah, thank you so much for attention. Yeah, do you have any questions?
Thank you, Valentyn. Are there any questions? Yes, there is one.
Yeah, okay, Q&A.
Do you see the question, or shall I read it?
Did you consider Judia parallel calculus,
Yes.
since your method is probabilistic, meaning it's so in our paper, we use the kind of potential outcome framework formulation, but I think Judia to calculus is essentially the same thing. It's just a different language to formalize the causal assumptions, but in the sense of kind of the like statistical inference or machine learning that we do with the data once we have assumptions, they're kind of all the same. So I mean, in our case, we say potential outcomes. In the language of do calculus, we would say the do operator. So in our case, we would be like, oh, how can we learn this treatment effect, which is the expectation of the outcome when we intervene on treatment, but also condition on the covariates minus the same expectation when we intervene on treatment and set it to control. So what the sensitivities can you
maybe
develop?
yeah, excuse me, Valentyn.
Or did I
maybe
answer it?
I'll read the question because the people who will watch afterwards will not understand what the question is. So about the sensitivity, since this is based on Gaussian noise, can you develop more on the complexity and tractability of the solution? Is it discrete integration? That's
a good question. It's a very good question. I'm not like super aware about the practical solution, so we definitely have a theory of how to get the differentially private meta learners. I think this the way Mareza implemented for example, this Gaussian noise perturbation for the output is like you have to sort of find the supremum over this joint space of treatment outcomes and covariates, and that thing maybe was not super stable. Yeah, so the actual practical application, like we are still not there. However, I think for the second case, it was fairly easier to implement. I hope I answered the question.
Yes, thank you. Thank you very much, Valentyn, again for joining our workshop. Thank you. It was a great pleasure to have you here.
Totally.
And yes, thank you. And I have great pleasure of introducing our last speaker for today. It's Denis Herasymuk, who is currently a PhD student at the New York University and is under the supervision of Professor Julia Stoyanovich, who is actually behind the very, very successful program of RAY for Ukraine, of which Tatiana will probably tell you more after this talk. But my pleasure is special because Denis Herasymuk graduated from our university, Ukrainian Catholic University, 3 years ago already. And I remember him, my student, who was always asked questions. So today I'll ask you more questions as well. So Denis this research of Denis is deeply rooted in responsible AI and trustworthy machine learning, with a special focus on responsible model selection. So today, Denis will present his talk, which is quite long, but smarter together, safer apart, achieving privacy and robustness in personalized machine learning. Denis, the floor is yours.
Yeah, thank you, Rostislav, for the kind introduction. So I'm happy to answer all your questions. So yeah, and today I want to present one of my papers, which I've done being a student at Imperial College London. And yeah, it's about achieving privacy and robustness in personalized machine learning. So let me start with the motivation. The first motivation here is that privacy matters. Modern software products should come with privacy guarantees, and we see a lot of examples of it. For example, in 2024, Apple announced their Apple Intelligence built on private cloud compute for end-to-end on-device and verifiable cloud privacy. And we also see a lot of other examples, for example, Brave, which is a privacy-focused web browser, or Gemma, which is Google's open weight model family, or one of the most recent trends, it's OpenClaw, which is privacy-preserving AI agent. And another motivation that personalization has become the new default. Companies want richer personal context, for example, to power agentic memory and adaptive assistance. And for that, they need to get data from clients to train their models. But this training on clients' data exposes models to adversaries, so robustness cannot be an afterthought. Also, we get a fundamental trade-off in this space that more personalization demands more shared personal data. Thus, in this work, we set the following research question. So how to build a personalized model per client under privacy and robustness guarantees, deployable on resource-constrained devices. So let me define our problem statement. So in our problem, we consider M clients, each with local data from a personal distribution. So our goal here is to train personalized parameters that minimizes local expected loss of each client. So basically, we don't try to train one consensus model that satisfy all clients. We try to train M models, basically one model per client. And we have two constraints, one differential privacy constraint. I am thankful to the previous speaker for defining it. And another constraint, it's robustness against up to 30% of malicious clients. And in terms of setting, we use fully peer-to-peer setting here. This means that we have no central server, and we need to use only IoT-grade compute for this training. Thus, it defines the following 4 key technical challenges. The first one is that it's that effective personalization should be done without a central server. This means that this clustering which we use should be done without central server, and we need to come up with such pseudocode for that. Another challenge is that we should preserve data privacy. And previous studies showed that if we add differential privacy noise to model gradients, it degrades accuracy, but it does degrade accuracy even more severely in peer-to-peer than in centralized federated learning. So we should overcome it. The third challenge is that we have resource constraints from practical side. This means that our training procedure should converge in a few rounds with minimal compute and communication overhead. And the last challenge is that we should be robust to different data and model poisoning attacks. So let me define our solution. So we propose P4. It's a training procedure for such type of threading. And basically it consists from two phases. So phase 1 is group formation and phase 2 is co-training. So in phase 1, our goal is to privately group clients with similar data distributions without a central server. So why grouping matters for personalization? And the reason is that if we randomly cluster our clients, at the end we can get models that perform even worse than we just simply train models on local data of these clients. And the reason is that local distribution of clients can be very different, so it's very non-IID data. And we should come up with some proxy to group these clients. And in our case, you use L1 normal distance between local model weights. How it works? Basically, before grouping, each client uses the same model architecture and does one global iteration and training on local data. After that, it adds gradient clipping and differential privacy noise. And after that, we get these models with differential privacy noise. And after that, we measure L1 norm distance between their model weights and construct the defined number of groups. And since we use differential privacy, we show in our paper that it satisfies differential privacy guarantees. And we also came up with a lightweight protocol how to group these clients based on these similarities, but you can look at it more in the paper, just how we group them in the defined set of groups. So phase 2, it's basically co-training. So it's how we train our models inside each group. One important note here is that for each client, we have two models, one proxy model and another local model. And why we need two models? Proxy model is basically that model which we train with differential privacy noise and gradient clipping. And basically we use this model to share our gradients with other clients. After that, these gradients are aggregated and models can continue their training using this model. Another model is clean model. Basically, it never leaves the device, and the main goal of this model is to capture personalization. So we don't add any differential privacy noise. It basically just trains on local data. And once again, here we use differential privacy, thus such training and model weight sharing satisfies privacy constraint. And we also use knowledge distillation between these two models in each client. So basically, the goal of this knowledge distillation is that local model can also get some extra knowledge from other clients. Since it only trains on local data, it should use some way to extract extra knowledge from other clients. For example, if local data doesn't have enough samples for specific classes, this knowledge distillation from aggregated proxy model can help us to get this knowledge and make the model more performant. And the last note is that we also have group aggregator for each group, and it's just one of the clients and that aggregates these models. And we rotate this role over this group, and we do this rotation just to balance overhead. And we also have several layers of defense against different poison attacks, and all of them use our advantages of previous two phases. So the first layer of defense is simple anomaly detection. Basically, if malicious client sends some random weights for aggregation, we're able to detect it with 3 sigma rule on L2 distance between local model weights. And this approach worked quite well for different model poison attacks. Another layer of defense is mcrew. It's existing robust aggregation, and we found that it works quite well with our threading, and it basically selects the M updates whose neighbors agree most and discards outliers before averaging. And the last layer of defense is client self-defense. Basically, we don't add anything here. We get it from our local proxy separation. Basically, we show that this KL knowledge distillation also can help with client self-defense. For example, when proxy model is poisoned, our local model is always clean. And this means that this knowledge distillation between local to proxy can also help proxy model to become more clean. Previous two layers also leverages advantages of our phase one, basically clustering, because in our clustering, we assume that local distribution of clients is similar. And in such a way, we are able to more easier identify outliers. And in terms of experiments, we done one experiment with privacy utility amplification. So basically here we have a set of baselines comparing with our P4 algorithm. We use several data sets from image classification and different types of models and different non-IID settings, how we split this data to be different on each client. And all models use, all settings, all baselines use the same differential privacy noise. And in the setting, we show that our method is able to achieve better accuracy than any other method under differential privacy constraints. And another experiment is where we show that our method is able to tolerate data poisoning attack and 3 model poisoning attacks. Basically, here we show that under 30% of malicious clients, our method is able to tolerate less than 10% of successful attack rate for all these different data sets and all these attacks. And from resource constraint perspective, we show that if you deploy our algorithm on Raspberry Pi, we get the following metrics for runtime, memory, power, and bandwidth, and all of them satisfy as a constraint for IoT-grade compute. And actually, that's all. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Dennis, very much. Are there any questions? Yes, there is one. I'll read it aloud. So, Dennis, this question from Munir about the anomaly detection layer. Do you consider the anomaly versus novelty trade-off, since new drifts may uncover new insights about user localized model, making learning or unlearning methods?
Yeah, it's more about drift. So basically, in our case, I believe we don't have any drift in this case. But this drift, I believe, if it appears when before client grouping, so basically those drifted models will be set to another group. This means that this drift should not impact our existing groups. For example, even we will have some new clients that appear in the system. They have completely different data distribution. So algorithm just puts them in a different group. And it can be even just one client in one group if we don't see any other similar groups for this new data drift. And in such a way, this drift will not impact our existing groups. So it's even just simple grouping will help here. But in terms of anomaly detection, here we assume that, for example, if attacker, firstly, before grouping, it provides normal gradients, and after that we just group them, and after that during this co-training phase, we get this malicious model poisoning attack. So anomaly detection helps us now to filter out this malicious gradients.
Okay, thank you. And I promised a question from myself. So as far as I understand, on this first phase, when you perform grouping, you probably treat all features equally, but what if some of them are not important at all? Then it creates too many groups, which is probably not desired. Or maybe you can use more sophisticated metrics, which also considered a correlation between different features, so not just Euclidean distance, but something which inherits, so say, is trained on the distribution itself.
More improved features. Okay, yeah. So what I can say here is that we don't basically use features for this clustering. We use model weights. We don't, so we don't share data for clustering. So our clustering also satisfies privacy constraints. So basically, we have our data. Well, we train our models on local data, add differential privacy noise, and then add gradient clipping, and after that use L1 distance between those model weights. And we show that in paper that just this one global iteration of training local data and this one L1 norm between local model weights can correlate with personal distribution of each client. In terms of more improved features, actually we does use them. I just didn't want to explain it in many slides. So basically, instead of raw data, each client uses some transformed features, which is called wavelet features, that captures different edges and textures of images, for example. And these features actually help us to reduce the size of our model, which we use on clients, because we also wanted to satisfy some IoT grade compute. And the second advantage is that using these features, we will need less number of epochs for training, and it gives us advantage for differential privacy, that we will use less epochs, and each epoch has its differential privacy cost. Therefore, we will need to add less noise. So basically, these extra features we use more for improvement of differential privacy training, not clustering, I would say. Yeah, thank you for your question.
Yeah, thank you, Denis, very much for a very nice presentation. I don't see any other questions, so thank you, Denis, and all the speakers of today's workshop. Thank you very much. You made it a great event. And with that, I pass the word to Tatiana and to Joseph for concluding words.
Start, Tatiana.
Yeah, I can start. So I want to thank too, like as Rostislav, to all our speakers today for their insightful talks, and to all our participants for their really great questions. This workshop reminded us of the importance of safe and secure AI, not only from technical challenge, but also as a question of trust, responsibility, and societal impact. From Ukrainian perspective, it's really important because Ukraine rebuilds and transforms its institutions now, and we need to engage with AI not only as users, but especially as researchers and partners shaping these technologies in a really responsible and safe way. It was already mentioned, but at the Ukrainian Catholic University, we are beginning to address these questions through the newly established Center for Data AI and Society. And we see it's exactly as a hub coordinating and inspiring this interdisciplinary research and in this direction, and also like the part of the communication with society and the whole world. So if you're looking for a partnership, please let me know. And the last thanks to our co-organizer from Ellis units in Prague and Alicante, especially to Nuria and Joseph for all your dedication in creation this workshop. I guess it was really great. Thank you.
Thank you very much. Nuria, would you also like to say a few words at the end?
I just wanted to thank you for including us and for bringing this topic this year for the workshop, and for your collaboration with the Human-Centric Machine Learning Research Program in Ellis, and also, of course, with Ellis Alicante. So I think it's been a great experience, and hopefully the participants have found these topics, interesting, and potentially new ideas or new collaborations might emerge from the workshop. So thank you to you for choosing this theme this year and inviting us, and of course to all the speakers and participants for joining, for several hours today.
Yeah, thank you very much, Nuria. It was a real pleasure. It was fantastic talks from you and all the speakers. And it was great to really do it together with the Human-Centric Machine Learning program. I think it made a total sense and it was great. I would like to again thank speakers, attendees. And just a final word, we hope to continue this tradition next year as well. We've been already thinking, what could be the topics. One topic which sort of resonates now with us, but also the broader community is AI for science. So I'm just sort of putting it here. We, of course, will discuss more, but, maybe this could be one of the candidates for the next year workshop. So thank you, everyone, again, and hopefully see you next year or even earlier at some physical events. Thank you.